DC control system is a critical emergency power source for substation devices that protect and control transmission and distribution systems. The battery charger is a key part of the DC control system. This first part of the program will look at the functions and components of a typical substation battery charger. The key points that will be covered include the functions of a substation battery charger, the main components of a charger, and the function of each of these components. A battery charger serves several functions in a typical substation DC system. First, it converts an alternating current input into a direct current output. Second, the charger applies the direct current output to a battery and controls the output in order to keep the battery fully charged. The charger also provides some or all of the direct current to the DC load. The battery supplies the DC load only when the load exceeds the capacity of the charger, or when a power outage prevents the charger from providing direct current to the load. The chargers used in substations can vary in size and design, but most have some common components or features. An AC breaker is provided for connecting the charger to or disconnecting the charger from its source of alternating current. A DC breaker is provided for connecting the charger to or disconnecting it from its DC loads, which include the battery. A DC voltmeter indicates the charger output voltage being supplied to the DC loads. Normal voltage in this system is usually a little above mid-scale. And a DC ammeter indicates the charger output current being supplied to the DC loads. Normal current is usually fairly low on the scale. A substation battery charger will also typically have a switch or timer that is known as a float equalize switch. The terms float and equalize refer to two different charge voltage levels that may be applied to the battery. When the timer is off or at zero, the charger operates at a normal preset float voltage. When the timer is activated, the charger operates at a predetermined higher equalize voltage for the number of hours for which the timer is set. After the time elapses, chargers with a timer automatically return to the float charge voltage. Chargers with a switch must be manually switched to the float charge mode. In addition to the float equalize switch or timer, a potentiometer is provided for adjusting the float charge voltage. And another potentiometer is provided for adjusting the equalized charge voltage. In addition to all the components just shown, a charger may have a number of other components. Some chargers may have a pilot light. The light is typically on when there is an AC input to the charger. A charger may also have a ground fault detection system. The system on this charger uses positive and negative ground fault indicating lights. Both lights are typically dimly lit. If the positive side of the DC system becomes grounded, the positive light will glow brightly and the negative light will go out. If the negative side of the DC system becomes grounded, the negative light will glow brightly and the positive light will go out. This charger also has positive and negative ground test buttons. Each button, when pressed, will introduce a ground in its respective part of the system. The buttons may be used to check that the ground fault detection system and lights are functioning properly. Finally, a charger may contain a variety of alarms and relays, including a high voltage alarm and relay, a low voltage alarm and relay, and a power failure alarm and relay. The specific components can vary from one charger to another. It's good to learn which components are included on the chargers in your system. To a degree, this will determine which checks you will make when you service your substation DC control systems. This part of the program presented the functions of a typical substation battery charger, its main components, and the function of each of those components. The next part of this program will cover a typical DC control system and how the charger works with other components in that system. But before continuing, stop the tape and read the charger functions and components portion of your text and answer the questions provided. In order to clearly understand the role of a charger in a DC control system, it's necessary to know what a typical DC control system layout looks like and how the system works. This part of the program will describe a typical DC control system. The key points that will be covered include a typical DC control system layout and the principles of how the control system works. The first part of a DC control system is located at the AC supply panel that is the source of alternating current to the battery charger. A breaker in the AC supply panel controls the supply of AC power to the charger. The next two parts of the DC control system are located at the battery charger. An AC input breaker on the charger panel controls the supply of alternating current to the charger. A DC output breaker on the charger panel controls the supply of direct current from the charger. The direct current output from the charger may be fed to a DC supply panel or directly to the battery, depending on the system design. In the DC supply panel, a series of breakers controls the supply of direct current to the DC loads on the system. The battery may be connected to the DC supply panel, or it may be connected directly to the charger. Also, depending on the system design, a fuse, current limiters, or a breaker may be used to protect the battery from short-circuit currents. Here, a single fuse is installed in series at midpoint in the battery. Other systems may have slow-blow fuses or current limiters in both the positive and negative cables close to where the cables connect to the battery. This simplified illustration of the DC control system can be used to explain the normal operation of the system. The normally closed breaker in an AC supply panel allows alternating current to flow from the panel. The normally closed AC input breaker on the charger allows alternating current to flow to the internal components of the charger, which convert the alternating current to direct current. The normally closed DC output breaker on the charger allows direct current to flow to the DC supply panel, as shown here, or directly to the battery, depending on how the system is arranged. The normally closed breakers on the DC control panel allow direct current to flow to the individual DC loads on the system. The battery charger normally supplies direct current to the loads as needed, and to the battery in order to keep the battery fully charged. If something should happen to interrupt alternating current input to the charger or direct current output from the charger, the battery would immediately supply all of the direct current to the DC loads. The components of your DC control system may vary some from the ones illustrated here, but the principles of control that they represent are the same. The breakers in a DC control system are operated in a specific sequence when a battery charger or a battery is replaced. Because DC control systems can vary some from the example used in this program, it's important for you to become familiar with your company's DC systems and how they work. The typical DC control system layout shown in this part of the program and the explanation of how the control system works should make it easier to familiarize yourself with the specifics of your DC systems. At this point, stop the tape, read the DC control system portion of your text, and answer the questions provided. Be sure you understand the material before continuing with the next part of this program. One of the main functions of a battery charger is to charge a battery or a cell. But there are different types of charges that can be given a battery. This part of the program will address a type of charge called a freshening charge. The key points that will be covered include the definition of a freshening charge, when it's applied, and the basic steps for applying it. A freshening charge is a charge that's given to new wet charged cells before they're put into service. Wet charged cells are new cells that are shipped from a manufacturer already filled with electrolyte and fully charged. Although wet charged cells are fully charged when they leave the factory, they will gradually self-discharge until they're connected to a source of voltage that's higher than the open circuit voltage of the cells. As the cells discharge, sulfation occurs. The resulting sulfate crystals can be difficult to remove with normal charging and can prevent the cells from taking a full charge. For this reason, A freshening charge is typically applied to wet charged cells before they're put into service. A freshening charge is a higher than normal charge voltage that's applied to wet charged cells before they're put into service to ensure that the crystals are driven off the plates and that the cells are fully recharged. A freshening charge is also sometimes referred to as a boost charge or an initial charge. Before a freshening charge is applied, the cells must be properly installed. In addition, the shipping vent plugs are typically replaced with flame arresters. Also, the electrolyte levels are checked to make sure that they're above the top of the plates. Water is only added if the plates aren't covered, and then only enough is added to cover the plates. Of course, when you're performing any kind of work on a battery, be sure to wear the appropriate protective gear and follow the required safety precautions. After the cells are prepared, a freshening charge can be applied to the battery. The charge is applied at a voltage and for a period of time that's specified either by the cell manufacturer or by company requirements. In general, the freshening charge is determined by the maximum voltage that the DC system loads can tolerate or the maximum charger voltage if load is not yet connected. For example, the maximum allowable voltage for this system is 58.8 volts. Voltage any higher than this may damage the control and protection circuits. This voltage is divided by the number of cells in the battery to determine the maximum voltage per cell, or VPC, that can be applied. This battery has 24 cells. The maximum system voltage of 58.8 volts divided by 24 cells gives a maximum of 2.45 volts per cell that can be applied. Generally, a freshening charge at 2.33 volts per cell is considered the minimum acceptable charge level. The number of hours that the freshening charge needs to be applied is typically specified in cell manufacturer instructions, or it may be specified by company procedures. To apply the freshening charge to the battery, the float equalize switch or timer on the battery charger is switched to the equalize position. Then the equalizing potentiometer is adjusted to provide the required output voltage to the battery. The output voltage is indicated by the charger's DC voltmeter. In this example, the output voltage is about 55 volts. It should be noted, however, that many utilities feel that a charger's analog voltmeter is not sensitive enough to be relied on for critical voltage adjustments. In this case, the DC voltage output can be verified by connecting a precision voltmeter or multimeter across the positive and negative terminals of the battery or across the charger output terminals. It's often recommended that the voltage be checked at the battery rather than at the output terminals of the charger because of the possibility of a slight line voltage drop between the charger and the battery. If necessary, the equalizing pot is adjusted to get the precise charger output required. Once the output voltage is set, the charger is allowed to apply the freshening charge to the battery for the required period of time. During the freshening charge, one of the cells is monitored regularly for temperature. This cell is referred to as the pilot cell. The temperature should not be allowed to rise above a certain point specified by the manufacturer. Generally, this is 110 to 120 degrees Fahrenheit or 43 to 49 degrees Celsius. The cells are also watched for excessive or violent gassing, which can distort the plates, create a high level of explosive gases, or cause the electrolyte to overflow. The gassing shown here is normal. If the temperature approaches or exceeds the limit, or if overflowing or excessive gassing is observed, the freshening charge should be stopped immediately by turning the float equalize timer or switch back to the float position. The battery is left on float until the cells cool down to 100 degrees Fahrenheit or 38 degrees Celsius. Once the cells have cooled, the freshening charge can be resumed. After the battery has been properly given a freshening charge, it's typically placed on float charge. Freshening charge voltage and times can vary with the type of battery used and with the load limitations of the DC system. Be sure to determine the specific freshening charge voltage and time requirements for your system. This part of the program covered the definition of a freshening charge, when it's applied, and the basic steps for applying it. A charger may be used to apply two other common types of charges, a float charge and an equalizing charge. These two charges will be described in the next part of this program. But before continuing, stop the tape and read the freshening charge portion of your text. Then answer the questions provided. The previous part of this program looked at the freshening charge that's applied to wet charge cells before they're put into service. This part of the program will look at two other common types of charges that are typically applied to substation batteries. These are the float charge and the equalizing charge. The key points that will be covered include the definition of float and equalizing charges when each charge is applied and the basic steps for applying each charge. A float charge is a normal charge applied continuously to a battery to keep the battery fully charged. For a float charge, the voltage is floated at a fixed level slightly above the normal open circuit voltage of the battery. This allows the battery to draw just enough current to overcome its self-discharge losses and maintain a full charge. The float voltage setting is typically specified in cell manufacturer instructions or by company procedures. A general float voltage guideline for lead antimony batteries is 2.15 to 2.18 volts per cell. For lead calcium batteries, a general guideline is 2.17 to 2.26 volts per cell. For the lead calcium battery in this example, the float voltage is 2.2 volts per cell. This is multiplied by the 24 cells in the battery, for a total float output voltage of 52.8 volts. To apply the float charge to the battery, the float equalize switch or timer on the battery charger is set at the float position. If the charger float output voltage hasn't been set, the float potentiometer is adjusted to provide the required float output voltage to the battery. The charger voltage output is verified by checking the voltage across the positive and negative terminals of the battery. If necessary, the float pot is adjusted to get the precise required float voltage output. Another type of charge that may be applied to a battery is an equalizing charge. An equalizing charge is a charge applied to a battery to raise the specific gravity and cell voltages of weaker cells to a uniform level with the other cells. When battery cells are in service, the cell voltages tend to become unbalanced or unequal. In other words, the voltages of some cells fall below the level of the others. If this continues, specific gravity will begin to fall along with the voltages. In general, if the voltage of any cell falls below 2.13 volts, or if the specific gravity of a cell falls 10 points below its full charge value, an equalizing charge should be given to the battery. The equalizing voltage setting and the number of hours that the equalizing charge is applied are typically specified in cell manufacturer instructions or by company procedures. A general equalizing voltage guideline for lead antimony and lead calcium batteries is 2.33 volts per cell. This is multiplied by the 24 cells in the battery, for a total equalizing output voltage of 55.92 volts. To apply the equalizing charge to the battery, the float equalize switch or timer on the battery charger is set at the equalize position. The equalizing charge is applied continuously for 35 to 70 hours or longer. If the charger equalizing output voltage is the same as the freshening output voltage, the equalizing potentiometer will not need to be changed. If the equalizing and freshening output voltages are not the same, the equalizing pot is adjusted to provide the required equalizing output voltage. As usual, the charger voltage output is verified across the terminals of the battery. During the equalizing charge, the same conditions are monitored that are checked during a freshening charge. The pilot cell temperature is noted regularly to ensure that it does not exceed the maximum allowable temperature, and the cells are watched for overflow or excessive gassing. If the temperature or gassing is excessive or if overflowing occurs, charging should be stopped until the cells cool to about 100 degrees Fahrenheit or 38 degrees Celsius. Then the equalizing charge can be resumed. As with the freshening charge, Float and equalizing charge voltages and times can vary with the type of battery used and with the load limitations of the DC system. Be sure to determine the specific float and equalizing charge voltage and time requirements for your system. Now, in order for a charger to provide the required direct current to the battery and the loads in the DC system, it must be properly maintained. The next part of this program will cover charger inspection and adjustment. Stop the tape now and read the float and equalizing charges portion of your text and answer the questions provided. All chargers require periodic inspection and adjustment. Proper maintenance will prolong the useful life of a charger and the battery that it serves. This last part of the program will demonstrate some basic battery charger inspection and adjustment tasks. The key points that will be covered include inspecting general charger conditions, checking for AC current and AC voltage output from the charger, checking float and equalizing voltages, and checking the calibration of the charger's voltmeter. Routine charger inspections and adjustments are typically done while the charger remains in service, so internal terminals will be energized. As usual, all required safety precautions should be observed. In general, charger inspection and adjustment steps can be done in any sequence. A good place to begin is to check the charger for signs of excessive heat. The outside of the charger can be felt to determine if the charger is too hot. Excessive heat may indicate faulty internal components, poor internal connections, or poor ventilation. Excessive heat can result in charger failure. To ensure good ventilation, the area around the charger should be kept clear so that nothing interferes with the free flow of air. In particular, the ventilation openings in the charger cabinet should be checked for obstructions. The interior of the charger is also checked for signs of heat, such as discolored terminals. Heating at the terminals is an indication of corroded or loose terminal connections. Any loose connection should be tightened. If necessary, the terminals would be cleaned using the appropriate tools and observing all other required safety precautions. A common cause of heat is dust buildup on surfaces designed to dissipate heat. Dust should be removed regularly. The internal components may be brushed, vacuumed, or blown clean. In addition to inspection and cleaning, the charger output voltage and current are noted and recorded. Any variation from the normal operating ranges should also be noted. On a periodic basis, it's a good practice to check for AC voltage at the battery. If a charger starts to go bad and loses its ability to convert AC to DC, it will show up at the battery. A meter, such as this digital volt-o-meter, can be used by setting it to measure AC voltage and placing the test probes across the terminals of the battery. The AC voltage reading here is within reason. If a charger is going bad, there will be a large AC voltage output from the charger, and the charger would need to be replaced. The float and equalized voltage settings should also be checked periodically. This can be done using a precision voltmeter or multimeter that's switched to a DC voltage setting. The voltage is checked with the charger in the float charge mode. In addition, the charger output current should be close to zero, indicating that the battery is not discharging. If necessary, the float voltage potentiometer is adjusted to provide the required float voltage output to the battery. The voltage is also checked with the charger in the equalizing charge mode. Again, if necessary, the equalizing voltage potentiometer is adjusted to provide the required equalizing voltage output to the battery. After the equalizing voltage output is checked, the float equalize switch is returned to the float charge mode. In addition, with the voltmeter still connected across the terminals of the battery, the calibration of the charger's panel voltmeter can be checked. If the panel voltmeter doesn't agree with the portable voltmeter, the panel meter is adjusted until it matches the reading on the portable voltmeter. This is done by turning a zero adjustment screw at the panel meter using a screwdriver. Finally, if the charger is equipped with alarms and protective relays, the operation of these devices may also be checked according to charger manufacturer instructions or company procedures. All checks and adjustments made to a battery charger should be accurately and thoroughly documented. These records serve as an invaluable tool for determining what additional attention a battery charger may need. Inspection, maintenance, and adjustment tasks, such as those shown in this part of the program, help to ensure that a charger provides the necessary DC power to the battery and to the other DC loads. A properly functioning charger is essential to ensuring reliable protection and control of transmission and distribution systems. Overall, this program presented basic charger functions and components, the layout and operation of a DC control system, common types of charges that may be applied to a battery, and charger inspection and adjustment tasks. In addition to the foundation provided by this unit on substation battery chargers, and for more complete training in substation battery systems, you may want to continue your training by learning about substation battery testing and by learning about substation battery, cell, and charger replacement.